In the last video, we have learned about the concepts of embedding and different embedding techniques. In this video, we are going to learn how embedding vectors are generated using Word2Vec models. So we will be exploring the Word2Vec model, especially skipgram model, and try to see how embedding vectors gets generated.
Embeddings or embedding vector lie at the core of natural language processing, empowering machine to understand the intricacies of human language. These vector representations enable machines to bridge the gap between raw text and meaningful understanding. As the field continues to grow, the magic of embedding will undoubtedly play a pivotal role in shaping the future of natural language processing. Have you ever wondered how these embedding vectors come into existence, or how these embedding vectors are acquired, or perhaps consider the intricacies of pre-training embedding models on vast corpora? In this video, we will unravel the answer to these questions. First and foremost, let's explore the significant breakthroughs in embedding technology throughout history. The bedrock of many embedding models, including those accessible via open source platforms, is rooted in these technological achievements. Consequently, when coming across or employing pre-trained embedding models on platforms like Google Cloud, Azure, AWS, Hugging Face, OpenAI, and others, it is reasonable to infer that they are constructed upon these fundamental technologies. To develop the intuition about how machine learns the context of human language or how embedding vectors are generated, let us try to explore one of the technique which was a major breakthrough in field of embedding, which is called Word2Vec. Word2Vec was created, patented, and published in 2013 by a team of researchers led by Mikolo at Google over these two papers. First, efficient estimation of word representation in vector space, and the second one, distributed representations of words and phrases and their compositionality. Word2Vec is one of the most popular pre-trained word embedding developed by Google that transforms word into continuous vector representations. It is trained on the Google News database about 100 billion words. It is a neural network based method that learns word embeddings by predicting the likelihood of words in a context window. Continuous bag of word, CBAW, and skipgram are two popular word embedding techniques that belongs to the Word2Vec family of models. So continuous bag of word, CBAW, is a model that aims to predict a target word based on the surrounding context or the surrounding word in a given window. So for this sentence, cat is a pet animal, it will try to predict A based on the surrounding words like cat, is, pet, and animal. On the other hand, skipgram reverses the CBO approach. It predicts the context word or the surrounding words given a target word. That means for the same sentence, which is cat is a pet animal, it will try to predict like cat is pet and animal for the target word A.
Now let us try to understand how training happens in skipgram. In the original implementation, they have used one hot encoding to represent each word in the corpus. But in my explanation, I am going to use the token value to make that explanation even simpler.
Skipgram is designed to capture the contextual information of a word by considering its neighbors. So let us try to understand skipgram model in detail. The skipgram model aims to predict context words given a target word. So generating training data for a skipgram word-to-vec model involves creating pairs of target and context word from a given text corpus. But even before the pairs-wise training data gets created, raw text corpus must undergo a text data pre-processing pipeline. This is the end-to-end pipeline for text data pre-processing, where this is the starting point and this is the ending point. In the text data pre-processing, we mainly perform these operations. So we do cleanup, normalization, chunking, and then encoding, where through tokenization, each unique word or subword is assigned a unique number. When we reach to the end point of pre-processing pipeline, this means that our data is cleaned, normalized, and tokenized, meaning each unique words or subwords is assigned a unique number. We call it token values. We will explore scriptgrams model concepts using a single sentence for illustration from our corpus. Let us see the high-level steps for creating training data for scriptgram model. First, for a target word, we need to decide a context window, also called rolling window, around the target word, like this. The size of the context window determines how many words before and after a given word are included as a context word of the given word. According to the author's note in their research paper, the recommended value is 10 for scriptgram. For instance, if the window size is 9 and the sentence is cat is a pet animal, and we are building training data pairs for the target word cat, the associated context word would be is, a, pet, and animal. The resultant pairwise training data would include pairs such as cat with is, cat with a, cat with pet, and cat with animal. Now we will shift the rolling window to the right, and our target word is. There is one token to the left and 3 tokens to the right, and we get our training data pair like this. So is cat, is a, is pet, and is animal. Again, we shift the rolling window to the right, and now our target word is a. There are 2 tokens to the left and 2 tokens to the right. We keep on moving our rolling window until we reach to the last word of the corpus. Finally, we end up having our training data set generated like this. So these are the token values of this pairwise data. So this becomes our training data as tokens. We are going to explore skipgram's word embedding model concepts using a single sentence. There is something called stop words, which are common words in English language that occur with a very high frequency, but carry much less information about the meaning of a phrase, especially in word embedding, where aim is to learn the relationships at word level and not at the sentence level. We should remove them. After removing stop words, our sentence is cat, pet, animal, and our skipgram model training data set will look like this. That is, for the target word cat, the surrounding word is pet and animal. Let us learn the architecture of skipgram word embedding model and try to simulate how exactly the training takes place. This demonstration will help us understand and answer these questions, like how machine learns the context of human language, or how tokens or words gets mapped to word embedding vector, or how embedding happens, or how embedding vector gets generated, or for that matter, how machine understands or learns the ambiguity, creativity, common sense, and diversity, which are the complex part of the human language. The skipgram is a neural network model which is surprisingly simple in its most basic form. If you try build a neural network for a skipgram, it will look like this. An input layer represents the target word, a single hidden layer. This hidden layer serves as the learned representations of the target word, and the output layer, which is a softmax to predict the context words or the surrounding words for the target word. Number of nodes in the output layer is same as the number of words in the corpus, which is also called vocab size. This is our original text corpus. In this corpus, we can see cat is the first word and dog is the last word. That is why in the output layer, They are put accordingly to make things simpler and clear for our understanding. Now consider this sentence: cat pet animal. This is our training data which we generated before. This data tells that cat has two surrounding words in this sentence: cat with pet and cat with animal. So 3 with 6 and 3 with 7 in the token value form. So the objective is to train this model such that when word cat is sent as an input, model should predict word pet as the surrounding word with the highest probability for the first sample and animal for the second sample. So when cat is sent, the model should produce this expected probability distribution. Here pet is expected with 100% probability as surrounding word for cat. So this is something like this. If we pass the token value 3, which is for word cat, model should produce value 6 in the output with highest probability. Here 6 is the token value for word pet. We cannot achieve this without having something in between to create the mathematical equation to produce such relation. This is where these weights comes into play. These edges are assigned with some weights. Now, using these weights, we can form algebraic equation like this to produce the expected result. This means cat multiplied by weight W1 plus cat multiplied by weight W2 plus cat multiplied by weight W3 produces highest probability for pet. Putting this in the token form, 3 multiplied by weight W1 plus 3 multiplied by weight W2 plus 3 multiplied by weight W3 should produce number 6 for word pet as the highest probability. When training process starts, at epoch 1, say these weights are assigned with value 1. Keep noticing this table at the right hand corner because I'm going to keep track of these learned weights there. So when weight is kept 1, it is producing value 9 in the output, which is the token value for word eyes. That means model will assign highest probability to word eyes as the surrounding word for input word cat. When comparing the actual result with the expected result, obviously this is incorrect. Therefore, through back propagation, these weights are adjusted for the second epoch. This time, the model is producing 8.34, which is more closer to token value 8, which represents word 2 in our corpus. This is still far off from the expected result because as per expected result, model should produce word pet with highest probability. Therefore, through back propagation, these weights are adjusted for the third epoch. This time, model is producing 5.85, which is very close to our expected token value 6 for word pet. And it is producing 97.5% of the probability, which is a very good probability to consider. Now you can imagine if this training process is continued for the whole word in the corpus, for every word, there will be these weights learned. Eventually, we will have this embedding vector for the whole word in our corpus, which is nothing but this learned embedding or the embedding vector. Just to note that for simplicity, I have considered only 3 nodes in the hidden layer. You can imagine if an embedding model has say 200 or 300 dimensions, these nodes will represent that many numbers. So each node of a hidden layer corresponds to a dimension. This is the process through which an embedding table is created when a model is trained to predict the surrounding word for a target word. Notably, our primary goal during this training was not to explicitly create this embedding vector. Instead, we began with a distinct problem, which was training a model to predict the surrounding words for a given target word. in the course of this training, the model naturally developed this embedding vector. Cool, isn't it? With the same intuition, you can imagine any other natural language training task and develop an assumption that an embedding table may be developed during that process. Take GPT models, for example, which are trained to predict the next word in the sequence. When this model is being trained on a vast corpus, an embedding model is generated as a byproduct. In essence, embedding emerges as a common outcome in various natural language training tasks.